Hi everyone, welcome to my channel. This is Mrs. Anderson, and in this video I'm going to go over how to graph a basic rational function. First thing I want us to look at is what the parent function of all of these graphs would look like. Now if you're not familiar with the term parent function, I'm going to go over what that means first. A parent function is the simplest graph that you could have for any type of function. And so we're focusing on rational functions, which would be functions that have fractions in them for this video. But it could be used for a linear equation, a quadratic equation, a cubic equation, a square root equation. Any of those would have parent functions. The parent function is, like I said, the simplest graph, and that means that there's really nothing affecting it. So there's no stretches or compressions, there's no transformations of the graph. It just is what it is. So the parent function for a rational graph looks like this. Y equals 1 over x, where x cannot equal 0. The reason that this one would be rational is because we have it written as a fraction. So I could put any number in for x, like 2, 3, 4, -2, -3, -4, and those would all be rational functions because they would all be fractions. Now, when you graph a rational function, you have two parts of the graph, and we kind of call those branches. So on this picture here, you should see those curved blue lines. Those are going to be known as the branches of the graph. Now, because we're dealing with a rational function, meaning if I start putting in a bunch of different numbers for x, I'm going to have fractions, or I would have decimals if I wrote them that way. So when we graph these, there will be a little bit of that where you'll have to estimate where you think it is on the coordinate plane. Now for parent functions, when we're changing them, or we're changing how they look on the coordinate plane, this is when we get into these things called transformations. Now, there's different types of transformations. You can either stretch or compress it, which would be making the graph become very tall and skinny, or becoming very, very short and wide. Or you can also translate it, which means that you move the graph around. So that could be going up, down, left, or right. I want to go over first how you decide whether something gets stretched or compressed. So that's based on the value that's sitting on top of the parent function. So before I had 1 over x. So if that value, they're calling it a here, if that changes, there's a couple different ways that it can affect the graph. So if the a, and we're talking about absolute value here, if the absolute value of a is greater than 1, so if it's 1.5, 2, 3, 3.5, 4, 4.5, so on, that's going to stretch the graph. That means that it's going to become tall and skinny. So it's going to make the graph move faster. If a is sitting between 0 and 1, so it would be 1/2, 0.75, 1/3, 0.6 repeating, that's going to shrink by a factor of a. So it's going to make the graph become very short. It's going to slow the graph down. Now if a is less than 0, that's going to reflect it across the x-axis. So you can look at that top number and it'll tell you how it's either going to be stretched or compressed. Now translation is all based on these two new values that they call h and k. And h is going to be on the bottom portion of the fraction with the x, and it's either going to be added or subtracted. And k is going to be on the outside of the fraction on the end, and that's also going to be added or subtracted. Now for these ones, x and the h, because they're both on the bottom, cannot be equal to each other. Because if I subtract that, I would get a 0 in my denominator, and we cannot divide by 0, ever. So you want to make sure that that becomes something that would be non-zero, or else you would run into a problem. So when we look at these two letters, the h and the h is going to shift the graph horizontally, so that means it's going to move it left or right, while k is going to shift it vertically, so that's going to move it up or down. Now we talk about these 2 points as being either vertical or horizontal asymptotes or asymptote, depending on how you hear it pronounced. So a vertical asymptote would be that h value at the bottom. So what you're going to see them do is set that x minus h portion equal to 0 and solve for x by moving the h over. And that's going to be your vertical asymptote. So that's going to be a vertical line that goes through a value on the coordinate plane. And then the horizontal asymptote is going to be the y equals k. So whatever that number is that's attached at the end of the graph, that's going to be the horizontal line. Now those asymptotes mean that as your rational function moves along the coordinate plane and it gets closer to those two lines, to the vertical line and to the horizontal line, it will never cross it. It's almost like a boundary, but it's like a force field of sorts where you cannot cross that line. It's physically impossible for the graph to ever reach it. It can get really, really close to it, so it's almost like that graph is going to just ride right along next to the line, getting closer and closer and closer, but it's never going to be able to touch it. So let's look at an example. This first one here, I have y equals 3 over x. So the first thing I want to do is find my asymptote. So to find the vertical asymptote, we take the x that's in the bottom of the fraction, and we, for this one, just have to set it equal to 0. So x is going to be 0. So that's actually going to be along one of the x and y axis here. For the horizontal asymptote, since there's no number added or subtracted to the end of this graph, it's just 3 over x, y is also going to be equal to 0. So your two asymptote lines are going to be at x equals 0 and y equals 0, which is going to be along the x and y axis. So in order to actually graph some other points, you're going to want to create a table that has some values. And you're going to want to pick some numbers that are above and below your vertical asymptote. So what that might look like is this table here. Now, my vertical asymptote is at x equals 0. So you can see in the middle of my chart, I have my x value being equal to 0, and the y value has those dashes through it. That's because I can't actually evaluate this function at x being equal to 0. If I try to take 3 divided by 0, if I try to plug that in, I'm not going to be able to evaluate that because we can't divide by 0. So you don't have to include that point in your table, but sometimes I put it in the middle and I just do those dashes there to kind of remind myself that that's the middle of my table to help me find values that go above and below, but I cannot evaluate at that point. So I usually just put the vertical asymptote in the middle, draw some dotted lines so that I know it cannot equal that point. That's my vertical asymptote. So numbers above and below 0 would be -1, -2, and then 1, 2. So what you're doing here now is evaluating the function at those points. So you're going to take -2, -1, 1, and 2, and you're going to plug it in for x in the equation that I gave you. So you're taking 3 over x, so 3 over -2, 3 over -1, 3 over 1, 3 over 2. And that's how I get the points -1.5, -3, 3, and 1.5. So now let's look at the graph. Remember, this is our function, y equals 3 over x. We said that the vertical asymptote was x equals 0, and the horizontal asymptote was y equals 0. Here's our table of values that we used, and so here's what the graph looks like. Now, you may not be able to see the horizontal and vertical asymptotes because, like I said, those are along the x and y axis. Normally what we use are dashed lines to represent those asymptotes. So you would see a dashed line going through the two axes there. Usually what I do if I'm graphing them by myself is I'll use a different color to represent the asymptotes. So I will do like a red pen or a red marker of some sort and draw those lines in first. And then I go in and I graph these points, -2, -1.5, -1, -3. Now you're not going to have a ton of points from the table that I created, but you could always add more if you needed to. But as long as you have a couple points to kind of see how the graph is going to curve and where those branches are going to go, you should be able to kind of show me how the rest of the graph is going to behave. And notice that for both of them that they're both approaching the x and y axis, but they're never going to cross those points because of those bounded areas. Let's look at another one here. So I have y equals 3 over x minus 1 minus 1. So I've changed my graph a little bit here. For the vertical asymptote, now I have x minus 1 in the bottom, so I need to set that equal to 0. In order to solve for x, we add 1 over, so we have x equals 1. So I'm going to have a vertical line going through the point x equals 1. Now the horizontal asymptote, I have a -1 attached to the end of my fraction part of the function, and so y is going to be equal to -1. Again, we're going to create a table, and I'm going to put in that 1 for that x equals 1 in the middle with the dashes, letting me know that that's that asymptote that I can't approach. And we pick numbers above and below 1, so 0, -1, 2, and 3. So the values I found are -2.5, -4, 2.5. Now, as these functions, if they start to get more complicated, you will want to use a calculator to help you evaluate them. Now, looking at the graph, we have that function, and we have our horizontal and vertical asymptotes with our table, and our graph looks like this. And you can see on this one that you do have those dotted lines at x equals 1 and y equals -1, so you can see how those lines were drawn in there, and then the branches were created by using the values in my table. If you're ready to give it a try, I've created a practice quiz on a website called Quizizz.com, and it's a multiple choice platform where you can go and practice the skill that you just learned. The link to that can be found below in the description, but I've also included it here in case you need to type it into your URL. I hope you learned something from this video, and thanks for watching.